This is a regular exercise. Every CyberGIS project meeting so far, I do this to update the community about the progress we've made recently, and this is mostly about the past year activity synthesized. And I'm presenting the progress, of course, on behalf of the project team, and we're really proud of this team assembled. It's a very exciting crowd. I'm privileged to be part of this team. I want to go directly to delve into what's left from Mike's talk the first day. He put forward this notion of discoveries, questions, predictions, and I highlight the killer problems. And this is also the bell ringing after the signs with the CyberGIS panel. In fact, the style I'm preparing this presentation is on the fly when I'm actually part of this meeting, gathering information. So if you see typos and mistakes, bear with me. Because the purpose of this presentation is to really capture not only our progress, but also the dynamics here, interestingly represented. So I want to share with you a small set of problems which I think are CyberGIS problems, or problems CyberGIS is uniquely positioned to solve, and the conventional GIS approaches either outdated or not positioned to solve. The first problem is a big spatial data problem, and last year, coming from exercise of the international conference tutorial, you remember this interface. This is the national elevation data sets. We assembled collaborating with Lynn Ursry's center and also open topography team at the San Diego Supercomputing Center. The idea is could you make this entire data set to the fingertips of anyone to be able to access a web browser coming into the system to analyze flexibly parts of the entirety of this, or even the computing power allows the entire data set for any user. And could we design a system like this with all the complexity managed behind the scene, while at the same time assuring the smoothness and the deliverables of results? We actually did it. And this opens up the possibility of understanding what are the user interfaces, what is the workflow management behind the scene we need to come up with. And as you learn from Lynn, there's new national elevation data sets program going to be based on LiDAR, and you learn from the keynote from Dave Tarbenton about TAU-DEEM and hydrological models from HydroShare. And this kind of interface and workflow, if we interoperate with the data sets and the analytics and modeling capability as we learn from these wonderful talks, and this is a big pathway for CyberGIS to move forward. And I don't think conventional GIS is situated to do this kind of work. Another kind of problem is a big spatial simulation. This is a picture created by Eric Shook. You heard his talk yesterday. And this is a simulation combines big data and computing intensive processes. In fact, you saw from the slide, there's population data sets, movement data sets associated with the model. And you learned this also from Li Yan's comments about coupled natural human systems and the dynamics, millions of agents you are moving about. And a comment from the audience is, do we have to do compromise, right? For gaining the scientific benefits because of the limitation of power of computing and modeling, we actually have to sacrifice the scientific understanding. And how many people are repeatedly doing those kinds of scientific processes due to the lack of CyberGIS? And this is an example. If we don't advance CyberGIS to the degree we like, we are always constrained to the level of details we're going to repeatedly do forever without the dramatic improvement of our scientific progress. So the third problem is what I call complex spatial decision making. You probably have visited this poster last night by graduate student Hao, is in the room, and Tao. They are working together, advised by a bioengineering scientist and also myself, to understand how you pull together different biomass, bioenergy information to optimize logistics, particularly supply chain, for making decisions about where biorefinery facilities are and biomass processing facilities are. And this is a complex problem because when you introduce this kind of new bioenergy facility network, you're considering existing energy infrastructure. So it's a whole set of different information you need to synthesize to come up with decisions of this type. And you need to engage different stakeholders to come to this environment. And the computing is very challenging behind the scene. And this kind of what I could even say yield-structured decision-making problem probably is not yet well tackled by existing GIS approaches. And I think CyberGIS is moving some steps forward to tackle this stream of problems. And this morning you learned from Wendy Cho from Illinois talking about this kind of a redistricting problem, and she shared with us her insights as we go to fine scale spatial units, we actually unleash the understanding of how this fine scale representation might give so many different options for us to make decisions upon. And the interface on the left is in fact a front end, because at fine scale at the moment we have no clue to report back the results, to have users interactively examine what's happening coming out of the computing processes. So right now we're working at coarse scale as a using computer jargon language debugging tool to understand the algorithmic behavior of this optimization process. And the computational approach Wendy was alluded to is what we call in the genetic algorithm evolutionary computation literature, it's called island model. So in fact, this is a deep spatial thinking into the design of computing processes. What Yan came up with is this asynchronous communication model across different islands of populations in the evolution of the subpopulations, because this is designed to be asynchronous and to be autonomous at individual island of populations. And this is scalable to very high performance computers. As we know, in high performance computers, one of the major bottlenecks is communication as you get into large scale calculations. So two examples from complex spatial decision making, and this example from ASU and Illinois' collaborative effort is what I characterize as collaborative knowledge discovery. This involves spatial statistics and data mining, but the idea is, could we act as a crowd, share models and specifications, and improve the specifications because of this mechanism existing? And it's really a knowledge production playground, and what that means in terms of accelerate scientific processes and improve the productivity. So this is what I argue is CyberGIS problem also. This is not something we've done in the project, but I will make a proposition based on my observations of what's happening. I think Don Wright and Mike Child have been quite active, as I know from Googling, as well as Tim Nigers had a presentation mentioning CyberGIS in one of the ESRI organized geodesign summit. My argument here is for this kind of process to come into play, GIS would need to be advanced into CyberGIS. And then I'll explain to you why after I refresh your memory about CyberGIS for what and whom. As you knew, this is our CyberGIS for 5 million users on the horizontal dimension. And vertically, this is CyberGIS going to the most advanced high-end cyber infrastructure environments. And in the between is what we approach as middleware. Again, to refresh your memory, in case you are not here on Sunday, this is the toolkit elements. We're approaching alpha release. And also the gateway, which is a browser online environment, consists of set of applications, relatively standalone, but has interconnections through services behind the scene. So coming back to this table I constructed as I was listening to all the talks happening this past couple of days, I think using the notion of that 3 elements in the CyberGIS project, if we analyze all the 5 categories of the problems which I tend to think are killer problems for CyberGIS to make contributions, you would see for the green color I'm using doodle pool fashion, if it's yes, maybe, or no. And for yes, that's clearly indicating, based on the progress we've made in the CyberGIS program, except for the geodesign, which is a proposition based on the similarities to the other kinds of problems. For big spatial data, you would need CyberGIS gateway. And you would need CyberGIS toolkit, and you would also need CyberGIS middleware, based on the experiences we have gained. And similarly, if you look at, say, complex spatial decision making, you maybe need a CyberGIS toolkit, but you would definitely need a CyberGIS gateway because that's the easy entry door for engaging stakeholders to specify their requirements and interacting with the decision-making environment. For geodesign, this is meant to have GIS exposed to designers. As we all know, designers are probably not well versed into the technical landscape of GIS tools. So you probably need a lower entry door. And as we know, this design is always an iterative process. You need to do many what ifs. And likely, if you are dealing with synthesis of knowledge and data, you would run into solving problems require high-end computing support. In fact, if we look across science and engineering, if we look at manufacturing design, those communities are well versed into high-performance computing because if you do prototypes, you don't want to mess up with the environment with preliminary designs, right? You want to run through many scenarios to compare with each of the scenarios against the optimal or suboptimal or ideal situations. This requires a lot of computational experimentation. So these problems I want to use to motivate our thinking. I think these are the problems I also tend to identify as not short-term problems. These problems are not going to be solved by the project of this 5-year cycle. And I think if we could make solid progress, we would be very delighted. And I'm positive we're making the desirable progress. Switching gear, a little alert here. And it's also a point of no return coming from this point. We're departing from science with CyberGIS and we're running to the wild digital world from this slide. As we understand, spatial temporal data in the geospatial domain is a very unique domain coming from the perspective of data science and fourth paradigm. As highlighted, this 6 dimensions of characteristics, if you compare with, say, astronomers' data, they are space-time data, but you could easily say they are probably not that diverse in terms of semantics or in terms of serving so many different kinds of applications. So I could use other examples coming from experimental experimental high-end physics, which is another space-time data world. But I think the argument here being special for dealing with geospatial, spatial temporal data in geospatial context is exciting and unique. So extending beyond the data world, what are the broad digital environments are we facing today? Well, again, point of no return. We are moving into the world of parallel computing architecture. This is not determined by GI scientists or geographers or geospatial scientists or technologists. This is determined by a much bigger computing industry. Moore's law physics, we basically had to switch to this term multiple years ago. And this means you have many cores, multiple cores, and you just need to work with this environment for new software to come and for new computing solutions to arise. And we continue to see heterogeneous architecture in this parallel computing world. It's not a single parallel modality. That's not the world we are having. It's heterogeneous architecture, and it's mobile, as Cyrus mentioned earlier. This is going wildly into many, many devices, and those devices also having multi-cores. And it's distributed. It's cloud and service oriented. So we have all of this. And most importantly, we are approaching what I call, or many others call, extreme scale computing information and communication systems all together. And GIS as either science or tools have no choice but getting situated in this digital environment. So give you one concrete example that I think mentioned earlier. This is a supercomputer funded by National Science Foundation. It's not on top 500 list because we decided not to go to that list because we think that measurement is not scientifically sound based on the different applications these days supercomputers serve. But interestingly, this system has balanced data and computing capability. And memory here is very impressive. I think it's, where's the memory? I believe it's 1 point something memory. Aggregated I/O and
top left.
Top left. This one, right? Yeah. So about 1.5 petabyte memory. So the reason I'm mentioning this is first because we are married with this parallel architecture. So that means our mainstream computing is consistent with high-end computing from computer architecture point of view. And today, my device was a supercomputer 10 years ago. So in 10 years, your device will be a supercomputer. So how do you work with an extreme scale system like this? It's literally planning for science and engineering and research in this kind of digital environments. And we know for sure, unless some major breakthrough of physics, we're going to be married with quantum computing or others. This is the architecture we live with. And this is the architecture we're going to show up on this device in some years, not too far. So I'd like to borrow what Mike had. Mike used this example to argue we need to have a holistic representation that may not be sensible to do divide and conquer. My argument here is it's okay to do divide and conquer, even if you want to gain holistic understanding, because in my work with Mark Armstrong, I argued when you do divide and conquer, you actually are not dividing and conquering the problem alone. You are dividing a spatial computational domain, which is a tier of knowledge established to serve these two principles. I'm not going to read, but one is focused on spatial, the other is focused on computational. So in the multiple decades research of computational geography, people have been focusing on decomposing problem itself without paying attention to there is necessity of establishing this spatial computational domain to bridge the spatial problem, which you could still solve holistically, but bridging to the underlying computing architecture, which could be parallel or distributed, that would be dependent on this domain to guide that problem-solving process. Of course, sometimes you would need to do approximation, but once you get into computer, even if you don't do parallel computing, you're doing approximation. That's discretization, first place. So an example of achieve holistic problem solving at the same time introducing the notion of spatial computational domain is for an agent-based model like this, you have objects, fields, agent is usually represented as objects, and your first order representation, say, is this lattice representation or raster representing the environment. But the next order of representation should be your spatial computational domain that bridges between the spatial domain representation and the computational processes and the computational representation. That's where you would figure out, broadly speaking, which I'll mention this slide first, which I think we have a rich opportunity here to pursue spatial computational principles and theories by bridging these two realms. Not only consider just dividing and conquering for resolving the problem size, but also to assure the consideration of spatial distribution, heterogeneity, and so forth, and also in the computational realm, uncertainty versus validity, performance versus reliability. I think this is increasingly important when we approach extreme scale computing information and communication systems. So in the literature, when I posed the necessity of spatial computational domain as a crucial knowledge area, I used this as a motivation. A question we would pose, say, what is the nature of computational intensity of a geographic analysis? Why spatial is special? That is comparable to the question in computer science, which is their foundational question for a half century or more. What is the nature of computational complexity? We always throw out the notion, say, oh, this problem is computationally intensive. What do we mean by that, right? What is the characterization of a problem with respect to computational intensity with relation to spatial characteristics? So I think this is a very rich area for new principles and the theories to be developed. And for graduate students, I encourage you, pause a little bit here to think deeper. So now coming to the science of CyberGIS, which I pose some challenges for us to think further in terms of the first one is scalability. So a lot of things, as yesterday we were discussing, we solved that problem before. That algorithm existed. So what? What do we do new here? Well, if you consider that extreme scale we're talking about, if you want to have your solutions, you have your data sizes, you want to have the number of users you want to engage, the scale makes the biggest difference. Those are the problems we have not solved. And we have to really think through what this means. And one example was when we were working with USGS on the p-raster blaster, that algorithm scaled okay on a local cluster between 2 dozens to 3 dozens processor cores. Now, once that algorithm moved to teragood machines, it behaved badly. And what was figured out was the spatial domain decomposition, which I argue should be decomposition of spatial computational domain, was not considering the marginals across the domain. And when those marginals accumulated too much at extreme scale, not even extreme scale, about 100,000 cores, you run into problems, you run into errors, you run into performance bottlenecks. So this is the kind of scalability we cannot take for granted and need scientific experimentation to understand the behaviors at a large scale. Usability. So from the step, you have a parallel algorithm running on GPU for viewshed analysis to make that algorithm utility available to hundreds of users and be able to still convince that algorithm produces right results for the mass is very different problem. And what to expose in this deep workflow for making sure the science is done right. I remember one of my graduate students, the first time we had Oak Ridge National Lab, the CyberGIS meeting, once she presented the viewshed analysis algorithm code results, Mike said, hey, I had a question. Why you got it so fragmented on the terrain? And then the students talked to Mike, gained probably some years of Mike's knowledge when Mike was doing viewshed analysis. So when that step passed, guess what? We've done almost more than the work that student did to make that viewshed algorithm well integrated through the GISolve middleware into the gateway. And that's not a complex analysis, believe me, compared to the problems I was sharing with you. But it was hard. It was very hard. Interoperability, of course, we're in an ecosystem. You have HydroShare, you have different other applications, you have different platforms, different services, and these systems are developed simultaneously with little consideration of other existence, at least from the historical perspective. Now we're moving to a new world. There might be difference. So we did some exercise with Esri colleagues, Steve Cope and Don Wright participated. This is mostly on the data interoperability side, figuring out license, access, presenting the data, metadata, and moving between the gateway and the ArcGIS Online. And Minghua was the one pulling the pieces of this puzzle together. Again, if you consider this to be a recipe for maybe other systems to interoperate with each other, there are a lot of things involved. And if we add analytics on this side, workflow composition on this side, community knowledge production environment on this could be very interesting to consider interoperability. Well, if Gateway, after 5 years, funding's gone, and there are some ArcGIS users benefit from some gateway services, we're not reliable anymore. It's gone. Sorry. So, in a system of systems context, how do you assure critical services and systems, they stay up? When you make that contact, establish that connections, those connections are going to persist and deliver the quality of services and results as advertised. And maybe advertisement is not always true, as we learn from the business world. And reproducibility with the deep infrastructure software stack, as Ian showed you, in a supercomputing environment, you got hundreds of libraries loaded up. If I do analysis in the gateway for a problem, scientific problem, and then next day you go into the gateway, how could I be sure the same library code used to validate the results? And what this really means, what should I tell from CyberGIS point of view to users, to scientists, what to be exposed to them in this provenance or workflow management? I think we don't know yet. We're just beginning to establish the environment to ask and answer, approach these questions. Well, understanding of scientific processes in such a dramatically changing digital environment and associated problems, I think we come to start grasping what a scientific process means here, just by the examples I provided, right? How do you make sure the scientific findings being produced actually coming through rigorous vetting and validation? And I should again move this to an earlier part of my talk. This is very important, as we debated yesterday afternoon. A set of activities, as I was alluded to, earlier, we've been active in this space and took an opportunistic approach, delivered tutorials, and had a focus on graduate students mentoring, and Gateway itself used by students across campuses, had some earlier modules developed, and we need to do a good job in the future years to make sure those materials be vetted and shared to broader communities, and organized meetings as we're doing here, trying to increase the awareness of what this really means scientifically and technologically. But the major piece of this puzzle in terms of education and workforce development is really a challenge across the board. I do believe we need to rethink a lot of things we took for granted, and this is probably a very nice time for us to reflect collectively on what should be done. But as I emphasized, we're really talking about the next generation who needs to cut across aisles. This is not a single domain approach that will work. It does require partnerships because the environment we're really talking about for scientific problem solving and the discoveries are a multidisciplinary environment. I bring back this ecosystem notion I introduced in the opening talk I gave the first day, and this is really just speaking to a very small subset of the broad ecosystem, and you learned from Dan Kans, the program officer, this morning. And the question is, how do we approach the education and workforce development in this ecosystem? I think that's a huge question. I do not have an answer. I could confidently share, but I think there could be a lot of ideas we need to debate about and figure out some pilot work to pursue. And particularly in our project, this is the kind of environment we're working with in terms of education and workforce development, because you do need concrete technologies and concrete environments for students to learn what do you mean by CyberGIS. And from the top, this is really driven by scientific problem solving, potential discoveries, killer problems we could identify, and pushing down to the needs for, as the discussions so far have been happening here, space-time integration and synthesis, and going down to this, what I call the core of CyberGIS, at least represented by the current project progress, and to the bottom, this is what I refer to as extreme scale computing information and communication environments from the NSF flagship cyber infrastructure environment, exceed Nancy's co-PI for, and the Open Science Grid project. I'm myself involved before the beginning of that project through this point, and of course, so many different clouds you could have multiplied, subtract, add, create different ways of your understanding of what the clouds mean. Sustainability. We're year 3, and this is something we, in fact, in the proposal, we needed to provide our thoughts to what this means, and you heard also this morning from the program officer. This is something I think as a community in general in cyber infrastructure we are learning, and from our project point of view, intellectual frontiers is a top factor. Only you gain intellectually the benefits you could coming to the CyberGIS research, education, and we feel like this is going to make CyberGIS activities sustainable and CyberGIS environment or software infrastructure sustainable. And financially, the science challenges, I was attempting to share with you a set of problems, I think are long-term problems, and multidisciplinary and rewarding mechanisms is sometimes we tend to give us a hard time, say, hey, could you get to new discoveries? But I think other times we should relax that to say, if you could accelerate as a community, your discovery pace. I think CyberGIS has that characteristic as well. Reusability, saving the efforts to come to certain progress. I think that's also an important part of the education workforce development. Needs to be open, we recognize that, and of course social organizational strategies we've been employing in the project. I'm excited to share with you a piece of news. At Illinois, we started this campus-wide center. It's called for Center for Advanced Visual and Spatial Studies. This is what I believe a critical piece of the sustainability puzzle. If you could mobilize a campus like Illinois, a research university, demonstrate what CyberGIS is about, and engage the campus community, most importantly, both research and education integrated. And I think that has some implications and impact, as our program officer was alluded to. University has a role to play in this major evolution of not only CyberGIS, but cyber infrastructure. And this is really combining critical spatial thinking and digital thinking, and use integration and synthesis across the tiers of knowledge involved. And you saw from the right hand are some representative topics and projects I have been telling you about, a lot of which are being conducted in this CyberGIS project. This is not only the CyberGIS NSF SI Square project, but also a number of awards. We've been fortunate to have to share with you the progress summarized in this presentation. And we're very grateful for the generous support. Especially one example is the partnership with USGS. They've been contributing expertise, joining the project regular activities. I think that's an important part of the sustainability argument I was making. So true intellectual benefits through the collaboration. And also my lab, the folks working together, and you saw some of them, or quite a few of them here. And it's truly a pleasure and a privilege to be able to work in this group. With that, I'm wrapping up, and thanks for your attention. And